Okay, can you hear me?
Yes, sir, we can.
Uh-huh. So let's get started. So go ahead. Uh, let's get started right away with the questions. Does anyone have questions?
Yes, sir. I have I primarily have one doubt in like the CSTR problems.
Uh-huh. Which one?
So the just like so the ninth one.
Ninth one. So this is the the ninth problem, right?
Yes, sir.
Uh-huh.
So sir, in this the year part,
Part,
so it's
part
written.
A.
Yes, sir. So it's written that explain why the cell density can increase as the flow rate is increased. So,
Uh-huh.
but like if we write it mathematically, then we like for steady states in CSTRs, we used to write S equal to Ks into D by mu m minus D.
Uh-huh.
So as D increases, so S should also increase. That is the residual substrate should also increase.
That's right.
And then we used to write that X equal to YSX into SF minus S.
Uh-huh.
So ideally, SF minus S should decrease as S increases, and then X should also decrease.
Uh-huh.
So, but like,
Ideally.
yes,
So
sir.
that's why the question is asking you, right? And this has also been covered in class. So basically, I mean, if I can, this is the profile. This is the ideal profile. This is X. I mean, I'm just going to call it ideal, but we know what we mean by that. And S will kind of go um, very sharply like this and kind of like that. So this is S ideal. And by ideal, actually, I mean I should actually replace ideal by X monode. This is the prediction. I mean, the formulas that you are giving are the formulas for the monode model.
Yes, sir.
Now, this is actually a straightforward question about what has been done in class. Under what conditions does X actually start declining at low D? This formula was also derived in class.
Yes, sir. I'll just revisit it once.
I mean, we've not just covered the monode model, right? And we went on to
Yes, sir.
discuss. Uh-huh. So that is part A. But I should mention that part B and part C refer to something that was not explicitly stated in class, but it is a minor variant of what we have already done. So, and that variation is the following. Um, let me just put it down here. The Monod model actually says that everything is proportional to the growth rate. The Monod model says that the substrate uptake rate is equal to y xs multiplied by mu. And it says that the rate of product formation is y xp times mu. This is what the Monod model says. This is, of course, there is a third assumption the model makes, which I should also put down, and that third assumption is mu equals, it's an increasing function of s of the form mu m multiplied by s. So these are all assumptions. All three of these are the assumptions of the Monod model. Now, um, the first thing that we discussed, we had an entire, I think 2, 3 lectures on this, was that there are instances where the stoichiometric coupling breaks down. By stoichiometric coupling, I mean that these rates are not directly proportional to the growth rate. It is not a single reaction, there are multiple reactions. And the first variant for this was what was called the uh, the uh, it, this model was discussed in class plus m, where this is the maintenance rate. This was referred to in the class as Hertz model. This is all covered in class. Now it turns out, and so the name given, and I think I also discussed this in class, saying that, you know, if you plot, if you get data as a function of d, then Monod model predicts that Rs is basically equal to y xs multiplied by d. It's just directly proportional to d, simply because mu is equal to d. So this expression over here becomes Rs equal to y xs multiplied by d. But the experiment showed that actually the data looks like this. It is slightly translated. And therefore, one model to account for this is a model that says that actually Rs is not directly proportional to mu, but it is equal to a flat line which has y-intercept m. So it is equal to m plus uh, y-xs multiplied by mu. This was given to you as Pert's model. And then I also gave you an alternative to this called the Herbert's model, which I defined and I told you to work it out on your own. Um, Now, it turns out that there is a variant of this for product formation too. So just as the simple Monod model says that the product formation rate is directly proportional to mu, somebody came along and said, no, 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 Rp is not equal to yxp times mu plus some, let's say, I don't know, call that constant, say, small p, I mean, any other uh, word, any other notation you want. So this is just the analog of the Pert's model, right? There is a term that is directly proportional to mu, and there is a term that is independent of mu. So the first term is called growth dependent, and the second term is called the growth independent component. And essentially, this background you need to know to work out this problem. So um, essentially, in a chemostat at steady state, this will become equal to yxp times d plus p. And this is commonly known as, there is a name for this. This is actually known as Ludeking Piret model. So that's Leudeking and then dash hyphen Piret, Piret. Now, this is a purely empirical extension that does not necessarily reflect what goes on in reality, but it's like a slight extension of the model. And um, uh, the question that is being asked is, part A is where should you operate the chemostat to optimize the productivity of a strictly growth associated product. So basically what they're saying is if it is strictly growth associated, then basically this constant terms, I shouldn't use small p because I've already used it to represent the product concentration. Just call it, um, I don't know, use the word alpha for the time being. Um, actually, they use the term uh, beta is the term commonly used. But in any case, the first problem says that where will the optimum be if where will the maximum volumetric productivity of the product be if the you have a strictly growth associated product, which means that this beta is equal to 0, right? And the second question says that where should you operate the chemostat if the productivity is purely uh, the other way around. That means the beta is intact, but this first term is equal to 0. And just keep in mind that the volumetric productivity is defined as uh, volumetric productivity is defined as RP times X. You know, the specific rate of product formation multiply. Just as biomass productivity is mu times X, it is RP times X. Is that clear?
Yes, sir.
Any other questions?
So one more question. So in the seventh question, in the
Uh-huh.
same, uh, so in the mu net equation that is given,
Uh-huh.
is the minus KD like included in the denominator or is it like separate?
Oh, so this is the Herbert model, right? This was given in class. I mean, I think that again, it looks to me like, I think I basically defined the model. I mean, I told you that in the case of the PERT model, you basically assume that um, so this is the Monod model. Um, this is the Monod model that the substrate consumed is directly proportional to uh, the amount of biomass that you are making. Then the PERT model says that, so this is the Monod model. And then in class we discussed that because you find that its predictions are not uh, consistent with what one observes in experiments, what PERT did was he said, no, there is not a single reaction. There is a second reaction, S, that is converted to CO2, where this takes place at the rate M. And that's exactly what I presented in my, I think I've said that this is the PERT's model. You can see that this uh, um, this expression over here in green, this is the PERT's model. In addition to, there's a parallel reaction, if you will, which is consuming the substrate for maintenance. So this is PERT's model. But I also mentioned in class that an alternative to PERT's model is what is called the Herbert model. And that model says that basically it is not S that is converted to CO2, but in fact, the biomass that is formed, some part of it degrades, and that takes place at the rate KD.
Fine, so
So
got
you'll
it. So it'll be like it won't be included in the denominator basically.
It is just minus KD.
Yeah. So understood.
So I think that none of you have tried. This was left as an exercise. I mean, so when I've said something in class left as an exercise, that means you tried. It doesn't mean that this is not spoon feeding. I mean, the notion that I do one extension S going to CO2 and say that try X going to CO2, and that's obviously not the same. Um, I would have hoped that you would have tried it on your own. Uh, I mean, I'll be happy to address questions, but not do it. You following what I'm saying? Yeah. So try it out on your own. And I mean, there are two numerical problems. I don't know if you can make any progress unless and until um, you have really worked this out. So, I mean, these two models, they give some similar results and some dissimilar results. So, I actually also pointed out, I know this is all recorded. So, I also mentioned, well, I hope that this is one of the lectures that was recorded. I don't know if it is not recorded, but it is definitely in the written notes. This PERTS model has been discussed at length. And I have also, it is in written form, the Herbert model. I also mentioned in class that there is a problem with the PERT model. And because there is a problem, the problem being that because it's a first order reaction, substrate is consumed even if uh, there is no substrate in the environment. This is a zeroth order reaction. It leads to some really pathological behavior. And that does not happen in the Herbert model. So, is that part clear?
Yes, sir.
Okay. So, have you people actually tried to
So
solve
it
these
would
problems, or?
Yes, sir. I've solved like
Uh-huh.
I've solved the problems. So them were doable.
Okay, go ahead. Any other questions?
so we could also use the Herbert model in the ninth question to explain the dip in X, right?
Yeah.
Yeah.
So
Okay.
actually, the right explanation would not be in in terms of a mathematical model, right? I mean, you can just see there's a simple physical argument here. The physical argument here is simply that actually the substrate is being consumed. So the Monod model assumes that any substrate that is consumed is being utilized for growth. Both of these models are relaxing that assumption effectively. Well, the PERT model directly says that the substrate is being used for maintenance too. Whereas if you look at the Herbert model, it is, now I've erased it, but let me put it down here. Effectively, it says the same thing. I mean, it says that if I have S going to X, it is, this model is saying, so I mean, I'll just put them in different colors. This is the Herbert model, and uh, um, this. So this is PERT, and this is um, this is the Herbert model. So I mean, maybe I should just, the notation here is um, this is taking place.
So, but like, shouldn't we actually have, like, biologically speaking, shouldn't it be a combination of both of these, since like both these things should be happening simultaneously?
Yeah.
Like the biomass should be
So
degrading as well, and the metabolism should be happening as well.
so people have tried that. I'll be happy to put that paper also for those who want to read. Uh, that has also been done. So people actually say that neither one is right. But before you say that, you have to ask what is wrong with the Herbert model. I mean, for PERT model, I've already pointed out there is an obvious deficiency. Even if there is no substrate, it will allow substrate to be consumed because it's a zeroth order reaction. But you take any one of them in their entirety, and you can see that both are basically saying that substrate is not being used. Part of the substrate may not be used for effective growth. In the case of the Herbert model, it is a little bit tricky because it says that you make biomass, but some part of the biomass, due to endogenous metabolism, is lost to energy. So, if you want to be more physiological about it, you have internal proteins, you have internal amino acids, you have internal RNA that is broken down to produce energy. So that leads to a loss of biomass due to the conversion of pre-existing biomaterial into CO2. But that also effectively will lead to consumption of S, but not production of biomass, because you made it but degraded it. Are you following what I'm saying? So, in principle, either model can be used, and in fact, in a certain way, both models will work. That was the whole point of asking you to try it out on your own. Both models will account for this data that I've just shown to you. In other words, both will give you something that looks like this green line over here. Both will give, this is RS is equal to Y Sx times D plus some constant. That constant is M in the case of the um, the the PERT model, because it simply says that there's an additional quantity M substrate is being consumed at the rate M. But in the case of the Herbert model, it'll be proportional to this quantity Kd. It'll be proportional to the quantity Kd, and the proportionality constant will basically say that uh, the amount of biomass that you are losing at the rate Kd corresponds effectively to loss of biomass at the rate, not surprisingly. It will be Kd is the rate at which you're losing biomass. So that means that you're losing substrate. I mean, you have to work your way through it. You're going to lose it, I mean, at the rate Kd. Because Kd has units of biomass. And if you're losing so much biomass, that corresponds to the loss of Y-XS times the rate at which you're losing biomass. This is your loss of substrate. By loss of substrate, I mean substrate that is consumed but not producing any biomass. So, I mean, to the question, can we use this? Of course we can. But the question is, and the second question is, both are happening. But before you decide that both are happening, you have to ask the question, what is wrong with the Herbert model? Do you see anything wrong with it? And that you will only find out if you actually sit down and work your way through it, just as I did it for the PERT model. I mean, these exercises are given because hopefully um, the goal of giving you these problems is not to just, I'm not you know basically giving you stuff to memorize. I do one way, now you try it out the other way. Practice and see if you can solve it on your own. Now that will show you that there may be a problem with the Herbert model. Once you find out that there's a problem with the Herbert model, then you may decide that, you know what, I'm not happy with either one of them. I want some combined model that actually takes the good things in both and uh, mitigates the deficiencies in both of them. And I can happily send you the paper for that. I'll upload it. But that's correct. So is that clear?
Yes, sir. It is.
But you have to work it out. I mean, go back to the notes and see. There are points at which I have said, work it out on your own. those are points where you are expected to. I mean, like the Monod model, I worked out what is happening to the substrate, but told you to work it out for product. I mean, if you can't do that, then I think, you know, not in a good place. The whole point is, if I do something and ask you to repeat it for something else, uh, you're expected to go ahead and do that. Okay. All right. Next question.
I had a question. So for that, can you go to the problem sheet on the batch reactors? So
Uh-huh.
question number 4. So in this data for only X and S versus T is given. So for estimating Ks and K1 individually, it is not possible unless we like know some relation for H plus. We can estimate like the product of Ks into 1 plus H plus upon K1, but to estimate them individually, we'll need some relation for H plus probably at the beginning or end of the reaction.
Actually, so let me be honest with you. This question is actually taken from, I think, one of the textbooks. Um, so first of all, this question, anybody who thinks that you can get this data from um, a batch reactor is basically not thinking the right way. So this question is actually fundamentally wrong, in my opinion. Um, for the reasons that were discussed in class. So, in a way, they are uh, really pushing the limits of what you can accomplish. Um, so first of all, um, determining mu m is pretty straightforward, right? Um, that part obvious. I did not elaborate on
Yes.
that. Is that correct?
Yeah.
Now, in principle, once you know mu m, then the task at hand is to find out uh, basically Ks and K1. That correct?
Yes.
These are the two remaining constants. Now, if you do this experiment, and Shake-Flask experiments can be done at a fixed value of, um, you can fix the pH, right, by choosing the buffer appropriately. Then you can perform a series of experiments at every H plus. In principle, do you agree with me that you can fix the pH by choosing a buffer?
Yes.
Uh-huh. So that means that, suppose for the time being, that there was a way of finding out. So let's just call this. So let's just call this. No. Will it allow me? It's not allowing me to write on it. What the hell is going on? This is not helpful. Hmm. Um, this is very weird. Um, Actually, I'd like to be able to write on this, but
So you can take a screenshot and annotate on that probably.
I think it's helpful if I can. Home. So strange. Anyway, so this
So you can take a screenshot by just dragging the pencil from the bottom right corner.
okay, let's just uh, proceed with what we have. So this particular term, ks multiplied by 1 plus h plus divided by k1, okay, let's just call this ks effective, right? So at any particular pH value, if it is fixed, if you fix the h plus, then the value of ks that you will observe will be ks multiplied by 1 plus h plus over k1. So this is the effective ks that you can observe at a given value of h plus. I mean, is that, that's just a matter of definition. Now, assume that you had a method that allowed you to determine this ks effective at every pH. So you do an experiment at one pH, you find out the value of ks effective. Then you do an experiment at another pH. Again, you find out the new value of ks effective, and so on and so forth. If I had all these points, I mean, it's pretty clear that you can find out both ks and k1. Is there a problem with that? I mean,
Yes, sir, it's clear.
so that's all. All I'm saying is.
So, but even like with that, we'll have the same problem that we have with finding just KS, right? Like the time
Right. So
duration is
when
so small.
I started off by saying that you have to assume that there is a method of determining the ks from a batch run. Now, these people they claim that you can determine now the circumstances under which you can determine ks from a batch run are limited to those instances where the value of ks is relatively high. I mean, other than that, as I've told you, basically the culture grows effectively at mu equal to mu m, and the effect of ks is not felt except in a very small time interval, somewhere between exponential and stationary phase. So it lasts barely for a few minutes. But if ks is relatively large, and you have a significant time period during which uh, the cells actually show submaximal growth rates. In other words, maybe I should. I think all this is sort of. Let me see. It's actually covered. So here is the. Um, um, right, right here. So, um, so here are the variants. You can see when I discuss these variants. Just after that, I discussed. Okay, so here is the discussion that we did, and I basically told you that mm, um, where is it? No, slightly above. Here it is. So in reality, the cells follow the white curve for biomass concentration, right? They go up and then they flatten out. Now, uh, but it turns out that uh, basically this white line is showing you exponential growth literally till the very end, and then the exponent, essentially the specific growth rate, then goes to zero, but it goes to zero over a very short time interval. If ks is large, then it will not look like this. Then it will kind of so this is the case if ks is small, if which is almost always the case. But if ks is large, you will see something like this change from mu equal to mu m to mu equal to zero will not take place in a very small time interval. It will actually take place with another color, let's say yellow. It will look like this. So essentially, I'll put it here, mu equals mu m s over ks plus s. If ks is really, really small, let's say on the order of milligrams per liter, so if this ks is on the order of milligrams per liter, then basically this fraction, s over ks plus s, will not become less than 1 until s has values on the order of milligrams per liter. So basically, in this case, the white here, somewhere here, the concentration has become on the order of 1 milligram per liter. But by that time, you have so many cells that this 1 milligram per liter is cleaned out in just a few minutes and you rapidly go to the stationary phase. But supposing your Ks was on the order of 100 milligrams per liter, if Ks is on the order of 100 milligrams per liter, then basically by the time S reaches the value 200, 300 milligrams per liter, this fraction has become substantially less than 1. So you still have a lot of substrate when the specific growth rate has become smaller than its maximum value. So that's what happens then. You start seeing a decline while there is still a substantial amount of substrate in the medium, and then it'll go like this. And if that happens, in those special circumstances where Ks is large, you will see a significant time interval over which the presence of Ks is felt, in the sense that the growth is actually less than submaximal. In that case, you can find um, Ks. Well, I mean, by fitting the exact solution, which was also, I think, indicated to you. I think if you go back here, um, this is lecture 5, I suppose. I told you that you can get the exact solution by solving this differential equation. This was given in class. You know? So, and I even wrote. Can you see this? Yeah? Try it out. Or, find out the solution. It's just this J type hack where you integrate an equation. But the problem is it'll give you t as a function of x instead of x as a function of t. Regardless of that case, once you have the exact solution, you can use that solution to your data. Do you follow? Meaning, you can try to find out. I mean, do you know what I'm saying? I mean, if you have an analytical solution that describes a graph, then you can use MATLAB or any nonlinear regression techniques to fit your data to the right value of Ks and mu m. Mu m you already know, so you have to simply tell the software to fit it to the right value of Ks, right? So, stated differently, coming back to the problem, um, in this particular problem, Ks effective can be determined for every H plus, provided that Ks effective is sufficiently large. If it is sufficiently large, then you will have a significant period of time where you will see it actually showing submaximal growth rates and the effect of Ks is felt. And therefore, the graph, when fitted to the exact solution, will give you the value of mu m and Ks effective. So in this way, do the experiment at one H plus. Mu m you already know. Do the experiment at one H plus. Fit it to find the corresponding value of Ks effective. Then do it at another H plus. Find out the next value of Ks effective. Do it for the third one, the fourth one, the fifth one, and essentially plot Ks effective versus H plus. It should be a linear line which will provide you both the value of Ks and K1. Following what I'm saying? Is that making sense?
Yes, it's good.
I think what these guys are telling you to do, I mean, is, um, this to me is the. So first of all, the question is flawed in terms of I've never seen anybody successfully pull KS out of it. But what they are telling you is the following. Mm, Let me see if I can. Um, that's also I cannot see how you would pull this off. Um, um, oh, I see. Oh, I see. Okay. uh, the way they're doing it is as follows. Let me show you. So, so what they're saying is that you do these measurements over the course of the experiment. So what you have is you have mu equals mu m multiplied by s over ks 1 plus h plus divided by k1 plus s. This is the model. Now this is what I have called ks effective. Now what they're saying is that when you do the experiment, right, uh, uh, plot. So basically, you have a constantly changing, like I told you, if you have a sufficiently high value of this KS effective, mu will actually change with KS. So what he's saying is do the following. This is S, and this is time, and this is, let's say, log of X. Log of X will change continuously until it goes to the stationary phase. And let's say this is your value of S. So this is S, and this is ln of X. In one experiment, this is done at a fixed pH. So this whole experiment is done at a fixed pH. Now, what he's saying is basically what you do is if it follows this law, right? If you know, you have to first sit down from the data, from ln x, this data, you have to calculate mu. So essentially, take this data and from this data, get mu as a function of time. And that's because what is mu? Mu equals 1 over x dx dt, which is for a shake flask, which is equal to ddt of ln x. So that means from the slope of this graph at various times, you can find the value of mu at various times. So essentially, what you do is you plot, you know, s as a function of time, and you know mu equal to the rate of change of ln x as a function of time at various times. These have to be the same times. So, for example, at this time, find the slope of this graph. That will give you the value of mu and find out the value of s. Now, once you have this data, then you can, in principle, calculate. So, from this data, you can go to 1 over s of time and 1 over mu. And if you plot 1 over mu versus 1 over S. From that, you can determine the KS effective for that run. So if I plot, I have, let's say, a set of 4 points. I get a set of 4 points here. This is all corresponding to a single run. And if I plot, you can see that you go back to this equation. That equation implies that 1 over mu equals, let me just keep it within, you can see, okay, this equation implies any hyperbolic equation when put in the reciprocal form will give you a linear equation. This equation implies that 1 over mu is equal to Ks effective divided by mu m multiplied by 1 over s plus k, and that will be plus 1 over mu m. So you have now this series. When you plot them in this fashion, if you plot 1 over mu at various times versus 1 over s at those very same times, then this person claims that you will get basically a straight line with y-intercept 1 over mu m and slope equal to ks effective divided by mu m. Since you know mu m, you can estimate ks effective. Now this entire thing was done at a fixed pH. So you can do it at various pH values, one pH, second pH, third pH, fourth pH. So that means that so each experiment will allow you to find the Ks effective for that graph, for that data, for that pH. And then when you have a plot of that allows you to get a plot, you get data of this type. For each Ks, you get various values of, for various values of H plus. For each value of H plus, you get a corresponding value of Ks effective. 1, 2, 3, 4, then just plot it. You plot Ks effective versus H plus. And sure enough, you should be able to, because if the model is correct, you have Ks effective as equal to Ks multiplied by H plus over K1. So you have a straight line, you should be able to extract two parameters. Is that part clear?
Yes, sir. So I just wanted to ask that the case that you just showed us, in which the value of Ks was so large that that lnx was changing throughout the exponential phase. Do we generally see this biologically in real life?
I mean, there are cases. It's not that it doesn't happen. So can somebody mute themselves? I mean, so anyway, so in the case that they have given, you may see it, because when you change the pH drastically, it can have a profound effect on the Ks value. The Ks value can actually jump up quite a bit if you perform these experiments at non-optimal conditions. Because roughly speaking, what will happen is when you change the pH to suboptimal conditions, the enzyme that may be responsible for picking up the substrate, it gets deformed because it needs the proper pH to maintain its structural integrity. So in this case, it might go through. But like I told you in the class, for the vast majority, the Ks value is on the order of milligrams per liter. And if it is on the order of milligrams per liter, you're never going to see it. But I mean, it's pretty obvious that this method that they are suggesting, in theory, it'll work. Um, in theory, it'll work, but you can see that it will only work if mu actually changes with S, right? I mean, if you have this picture, the one that I showed to you, where S is declining, but mu is equal to mu m virtually all the time, you will not have any points. Where are the points where both mu and S are changing? I mean, where is it? Um, I guess it's way up there. Um, I have to go back to yeah. So if you take a look at this picture, the one this is the picture most of the time. You can see S is decreasing, but mu is equal to mu m. The only region in which S and mu m are changing and mu are changing is in that very thin regime between exponential growth and stationary phase. So the very few cases in which Ks is large, that's the only case in which both mu and S change over a significant period of time so that you can get like 4 or 5 points. And if you can get those 4 or 5 points, then the method that I have just shown to you will work. You basically, for each pH, you plot 1 over mu versus 1 over S for various points. That allows you to get Ks effective for that pH. Then you plot the Ks effective versus the pH and fit the straight line to the two constants Ks and K1. Clear?
Yes.
So I mean, it works, but I mean, I guess I mean, if I have to judge the value of this question in terms of uh, its applicability, there are very few cases where this will go through. But I guess there are instances where it will work. So go ahead. Next question.
So I had a very small question. In the CSTR problem set,
Uh-huh.
question number 2, I just wanted to know what Dmax is. Is Dmax the critical dilution rate or the
Yes, it's
optimal?
the critical dilution rate.
Okay, okay.
And it's the maximum dilution rate, right? That you can.
Yes, I just wanted to clarify.
I mean, you can operate it at higher dilution rates, but you will have no cells.
Yes, got it.
Okay. Any other questions?
So also, we refer to this term volumetric productivity very often in these questions, which is the product of D and X. I don't necessarily understand the significance of this. Could you just explain it once?
Well, the volumetric productivity is the rate of any entity, is the rate at which that entity is made per unit volume, per unit time. So it's a rate of production based on the volume of the reactor. You know, I mean, so I mean, and that's why I told you the formulas are then pretty straightforward, right? I mean, in every single case where something is being made, if you know its specific productivity, and the specific productivity is something that is based on the dry weight. So that's, for example, in grams per hour per gram dry weight, you simply have to multiply it by the biomass concentration to convert it into grams of that product per liter per hour. So, I mean, volumetric productivity is grams of product, and this product might be biomass itself, because biomass itself is a product of growth per liter. So, how much do you make? Actually, the right way to think about it is what is the rate at which the product is produced per hour per liter of reactor. And it is not difficult to see that this is equal to grams. Just think that this is not, this file has become too big. So this is equal to grams of product produced per hour, not per liter, but per gram dry weight of biomass, multiplied by the grams dry weight of biomass that you have per liter. So now just apply this to, let's say, if biomass, want to know what is the volumetric productivity of biomass? Well, the volumetric productivity, so volumetric productivity, so this term is known as, uh, this term is known as specific productivity because it's based on dry weight. The moment you see the word specific, you know that it is based on the total dry weight. For example, specific activity is how many units of enzyme you have per gram dry weight. You know, if you just say activity, it is how many units you have per milliliter of culture. So volumetric productivity is specific productivity multiplied by the biomass concentration. Now, um, let's apply that. So let's say we want to consider biomass. So let's just say we want to consider the volumetric productivity of biomass. Well, that would be how many grams of biomass you make per gram dry weight per hour. Well, that's nothing but the specific growth rate mu. Mu is nothing but how much dry weight you make per unit time per dry weight. It's the per capita growth rate. And that has to be multiplied by X. If I ask you for volumetric productivity of product, say ethanol or something, it is nothing but the specific productivity, which is RP. It has units of grams of product per, per per hour per gram dry weight multiplied by X. And now what that means in a particular reactor depends upon the configuration of that reactor. So in a chemostat, if mu is equal to D, then the volumetric productivity of the biomass is D times X. If Monod's model holds, then RP is simply, if Monod models holds, then in a chemostat, this is nothing but YXP, right, times mu. Because in a Monod model, everything is proportional to mu. And if you do it in a chemostat, then mu is equal to D. So this becomes equal to, so you keep applying what the condition is. So this is true if you have Monod model. If you had that Ludeking Piret model, it would be YXP mu plus beta. If you had only growth independent product formation, it would be only beta. What RP is depends upon the assumptions you make. And then what mu is depends upon the reactor you have. You put mu equal to D if you have a chemostat. But if you had a batch reactor, you're not going to put it equal to D, right? It's a completely meaningless. Is that clear now?
Yes, sir, it's clear now.
So has anybody solved? I mean, how did you solve this problem? I mean, problem number 4. How did you solve this problem? If people did anybody solve problem number 4? Actually, all this is even in the paper that I have given to you to read. The fact that nobody's even brought these things up. So, did anybody solve problem 4?
Yes, sir.
Okay, so let's hear. What did you get? I mean, do you have your answers in front of you?
So I didn't put in the values that were given in the question finally, but I did figure out how we would get the optimum for part B, and for part A it was pretty straightforward.
Um, let's see. Um, um, so, um, how did you get the optimum D? Um,
So I use the fact that x is equal to y as x into sf minus s, and since we know
uh-huh,
s in terms of d,
uh-huh,
since we already know s in terms of d, which is ks d upon mu m
uh-huh,
minus d, so I put
uh-huh,
that in into the equation. Then
uh-huh,
use the quantity d into x. So basically
uh-huh,
multiplied this entire equation by d, and
uh-huh,
tried to find out the differentiation of dx with respect
uh-huh,
to d, and
uh-huh.
equated that with 0. So I got
Okay.
what the maximum. I mean, so I got the point where we should get a D
And
optimum, and therefore through that I calculated.
so you calculated the optimum D, and then you calculated. So, if I were to, so let me push this a little bit further. So this is all there in the paper that you've been asked to read. Um, First of all, if you plot dx, right? So when you run an experiment, it'll give you x versus d, right? Keeping feed concentration fixed. You plot. So let me just if you so in a chemostat, if you plot, if you collect data as a function of d, and this is the fixed feed concentration SF, you get some concentrations of d. I mean, you get some concentrations of. So according to the Monod model, your biomass concentration kind of looks like this. This is X, and this is, let's say, S. Somewhere here, S becomes equal to SF, and this washout. This is this point here is the critical dilution rate. You're telling me that the volumetric, so the volumetric biomass production rate is mu x, which in the case of a chemostat just becomes d times x, and you know what x is, so that is d times. Let's see, it's not responding yet. So, so this is d times y sx sf minus s, where s is known to be a function of d of the form d over mu n minus d. So essentially, you get a function of d, you differentiate it, and you find out. Now, can I ask you uh, what the shape of this dx will look like? Anybody? I'm not asking anybody in particular. What do you think the shape of dx will look like?
So I think it'll start from. I mean, it'll have a maxima. So it'll start lower, it will go up, and then it'll come back down again.
Uh-huh. Well, but why?
So are you asking mathematically or maybe in
No,
a
no, no, no.
biological sense?
Physically, physically,
Oh,
physically. I mean, just tell me, uh, what is the value of dx? Uh, you know, so here's a straightforward one. When d goes to zero, what is the value of dx? Is anybody? I mean, if I make the flow rate go to 0, given the data
So
that I have
it
just
should
shown
be
to you,
0.
this is actually, and what happens when D equals DC?
Again,
What
it
will
should
be
go
the
to
value
0.
of dx? Huh?
Again,
Uh-huh. So, I mean, you can see that dx is going to be 0 here and 0 here. As in
yes.
between, I mean, are you guys also thinking about these things physically, or so naturally it will go up and then come down? It is only because of that you can apply the derivative method and get through with it. I mean, supposing it was, you don't know beforehand unless and until you think along these lines. What if dx was like this? Would your differentiation method work?
No, not in that case.
So in applying it, I mean, you have to first ask, right? Do you think your interior point? Do you think your optimal point is an interior point, right? I mean, if it is a boundary point, there is no point in differentiating. It doesn't give you any information. Okay, uh, so now we know why there is an optimum, right? Because I mean, at the left end, there is no flow. So D is equal to 0, you get no cells. At the right end, you have flow, but you have no cells. So either way, you get nothing. Your point is now when you go through these calculations, and these are covered in the papers that you were asked to read, they will give you the exact formulas for the optima. Um, um, so, what? How did you tackle? How did you tackle? Is anybody there who tackled the batch part? So I mean, when you do the um, differentiation. By the way, did you get an expression? Did you actually differentiate it and find the optimum D? What was
Yes,
the
so I did.
expression you got? What was the expression
So I got
you
D
got?
optimum equal to mu m into
Uh-huh.
bracket 1 plus square root of ks upon sf plus ks.
Uh, did you get plus or minus?
So plus.
That's a problem, right? You see what the problem is? Put a plus.
Yeah,
What is the
yeah,
problem?
yeah. If D optimum is supposed to be, if D is supposed to be equal to mu and mu has the maximum value of mu m, then D optimum here it shows to be greater than mu m.
I mean, the relative magnitudes of the quantities we have are on this axis. If D sub C is over here, then mu m is bigger than that. Why? Because D sub C is equal to mu m multiplied by SF over Ks plus SF. That is clearly less than mu m. It can be close to mu m, but it cannot be bigger than it. And we have just shown by this physical argument that your D optimum is somewhere here. But your formula is telling me that D optimum is bigger than mu m. Are you following what I'm saying?
Yes, I guess.
Uh-huh. So I think it should be 1 minus.
Yes, I think I might have made a mistake there.
Uh-huh. And that clearly means that your D optimum, if you put a minus, it's clear that your D optimum is less than mu m, right? Because you have a minus sign there. Is that part clear? I mean, the formula that you have just given to me is D optimum equals mu m 1 minus square root of ks over ks plus sf. This is the formula you've given. This is clearly less than mu m. Correct? Yes?
Yes.
Uh-huh. So, I mean, I'd like you to think, but is this expression D optimum less than D critical? Your D critical is equal to mu m multiplied by SF over Ks plus SF. Is it less? Can you check and see? I'm not asking you to do it right now, but I mean, somebody may want to see whether that better hold, right? I mean, I've just drawn the relative magnitudes and shown to you the picture that must prevail. So this is also, you know, the fact that D optimum is less than mu m comes straight out of the formula you have. Be interesting to see what is the relationship between D optimum and D critical. Where do they stand? I mean, your D optimum better be less than D critical. Is it or is it not? You can check. Okay. Um, yeah. So uh, the next question I had is, did anybody do the batch part?
Yes, sir.
Yes, sir.
Yes, sir.
Uh-huh. So what did you find uh, for the maximum cell density?
So the maximum cell density would be would obviously be at the end of the reaction, right?
Uh-huh. Uh-huh.
Where it is like x naught plus y sx into sf
So
or s naught.
that's how much was it? Yeah? See, this problem is about numbers. Yeah, it's not about staring at formulas. The whole point is to see what is the relative volumetric productivity in the two cases. And the reason why you're doing this calculation is at the end of it, you ask, but why? But you will never ask the question why if all you've done is calculated formulas. So, did anybody do numbers? It looks like, I mean, DVV, man, you know, numbers are not very popular.
So X max comes out as 5.
Yes, sir. 5 grams.
You got 5 grams dry weight per liter.
Yes, sir.
What is the, somebody just gave me the formula x0 plus yxs s0, right?
Yes, sir. Y sx, sir.
Uh-huh. What is the value of x0?
So inoculated with
1.
1 gram dry weight, so 1.
Uh-huh. 1 gram dry weight, yes. But in how much volume?
Right, sir. So it should be 0.01 gram dry weight per liter
Uh-huh.
cell
Now what's
density.
the answer?
So it should be 4.0.
4.01.
Uh-huh. So intuitively, that should make sense to you. Normally, when you do a batch run, you start with a really small amount, x0, and you expand that maybe 100-fold. In most problems, your x0 will be really small compared to yxs s0. You start with a really small inoculum and you allow them to go through 4 or 5 doublings. 4 or 5 doublings means it's going to go from whatever its initial value is to about 30 times its final value. That means that the initial amount is really minuscule compared to. So the 4.01 basically means mostly it was the new biomass you made. You started off with practically nothing and made a lot of biomass out of it. Okay. How much time did it take get to this point?
8.56 hours.
Uh-huh. So what was your volumetric productivity?
So it should be 4.01 divided by 8.56.
Uh-huh. Which is how much?
0.46 grams per liter per hour.
Okay. So it's about 0.5 grams dry weight per liter per hour. Is that correct?
Yes, sir.
Uh-huh. Can anybody do the numbers for the CSTR? So what is, D optimum? What was your D optimum? Actually, um, maybe I'll just move forward. Let's just say it turns out that um, the chemostat gives you almost um, um, 5 times. The whole point was actually calculating numbers, and they're asking the question, but why is the productivity in the chemostat higher? Um, that is the question that warrants some thought, right? You know now the expression. I just gave it to you. This is the expression for the volumetric productivity of biomass. Okay, is that part clear?
Yes, sir.
Huh. Now, um, if you operate the chemostat at its optimal dilution rate, you haven't done the numbers, so you have to sit down and think about this. Uh, why is it that this product is much higher than the case of a chemostat? That's the kind of question you'll be asked on the minor. Okay, so I'm not looking for some regurgitation of tell me what a chemostat is. It is going to be checking whether you've given some thought to, and the whole point of these problems was to let you think about the problems. So anyway, go ahead. I mean, I think 5 or 10 more minutes, after which I have to leave because I'm sitting somewhere. It's closing down. Any other questions? No further questions?
No, sir, nothing from your side.
Okay. All right then. Okay. Thank you. So, um, most probably we'll start around 2 p.m. on Saturday. And I will read the papers very carefully. Uh, I will not be asking you to reproduce formulas there. I will be asking you what do you understand of what is written over there, um, in 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 the Viva. Okay, so I think that these problems, if you understand them, if you knew what you were doing, this is goes a very long way in understanding both the papers. The first paper is on a chemostat. The second paper is on Pert's model of maintenance, and he refers to you know what Herbert is talking. And the third paper is the one that I covered in class on medium design. So I think all of this stuff was covered pretty thoroughly. So good luck. Study the stuff carefully. I will see you on Saturday. Okay. Thank you very much.
Thank you, sir.
Thank you.
So, could you please also share these notes?
Which notes? I've already put. I think the only the latter part of the course. Very few. I mean,
I think we only have up till lecture 5.